तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture we have been seeing about the flip-flops as against the latch. In a latch you store a bit 0 and a 1. In a flip-flop also you do that, but a flip-flop has an extra additional control called a gate, called the clock. When the clock is high, only then the data can be stored in the flip-flop, and when the clock is low, whatever has been stored will be retained even when there is a change in the input. We saw the basic SR flip-flop and the D flip-flop wherein single bit data can be stored with a single input, D input, data input, by connecting S and R through an inverter. Then we talked about the condition of 1-1 being not permitted for an SR flip-flop and see whether we can do something about it. So, we modified the input AND gate into a 3 input NAND gate, and we found that it is possible to have an operation corresponding to x is equal to 1 or is equal to 1, wherein the flip-flop output keeps changing constantly from 0 to 1 to back to 0 to 1 to 1 to 0, 0 to 1, 1 to 0, so forth, as long as the clock is high. When the clock is low, of course, it retains its content as a memory state. Now, the very frequent change of the output with an SR flip-flop with S is equal to 1, R is equal to 1 with an extra input to the input NAND gate is disturbing because we do not want that type of behavior. It is called raising, I said. Raising is not a desirable behavior. On the other hand, it is a nice idea to have a input condition with 1-1 where the output changes from the present state to the complementary state. If the state had an output of 1, we would like to have the output 0, and from 0 to 1 back and forth, 1 and 0, 0 to 1, provided it does only once in a clock cycle, in a clock period. So, we saw how to, we were thinking about how to prevent this raising, and one way to do it is to make a clock high period, the clock active period much smaller, very small, smaller than the propagation delay of the flip-flop, which is not a practical solution to the problem. There are a couple of other ways we can do it. One way is called the master-slave concept. So, what we will basically have in a master-slave operation, the input gates remember this, and this went to the 2 NAND gate combination. This is the basic structure we discussed in the last lecture, and this came from here and this came from here. Instead of that, what I am going to do is to extend this into one more stage of the same identical flip flop. And the output of this I will feed into the SR latch as we did earlier. This is the corresponding to the clock input. Now, I will, instead of tying the output of these 2 gates to the input gates, what I will now do is to take this all the way from here. After the second stage, I am replicating, I am duplicating this into this, except that I do not need 3 inputs, I need only 2 inputs, because I am going to give the external input only once. These are the external inputs, this is the input from the clock, this is the feedback. Now, output of this will be fed into this. Oh, this is the latch which part of this flip flop. Now, I will have an identical stage of flip flop where the output of this will be fed into this, output of this will be fed into this, and then I have this basic SR latch here. This output will go into this. I am taking the feedback all right from the output, but not immediately, but after one more stage. One more similar stage I put and then take the feedback. So, this I will now call Q and Q bar. These are intermediate outputs, and this also will be clock, but one thing I will do is to not connect the clock as it is into this. I am going to invert my clock and then connect this. So, I have more or less now a condition of 2 flip flops. The clock is common, but one of them is fed directly, the other clock is fed through an inverter. These are the 2 external inputs which we called S and R earlier. The third input comes from the output stage, but not immediately, but after one extra stage, a second stage. You put a second stage and take the output of the second stage and feed it back into the input. Now, this will behave exactly like the feedback flip flop we discussed yesterday, except that this output will change only once in a clock cycle. I will tell you why. Now, the clock has to be high for any for normal operation flip flop. That is what we said. The function of the clock is to enable the output to change as per the inputs when the clock is high, and not change the output when the clock is low, whatever be the input. Now, if that is the case, I am feeding a clock here, but an invert of the clock here. When the clock is high for this flip flop, it will be low for this flip flop. So, if you consider this as one flip flop, whose output is fed as input to the second flip flop, I will call this the second flip flop. This flip flop and this flip flop are identical. Of course, there is an extra input is there, the feedback input. So, this gate is a 2 input gate, this is a 3 input gate. That is one change, one difference, but that is because I can only I want the feedback only once. But more importantly, the difference between these 2 flip flops is that one has a clock which is high when the other is low, and vice versa. So, when the clock is high for this flip flop will change state, but this feedback is not going to happen because feedback is from here, not from here. So, this constantly changing, the raising condition is not going to happen. Only when the output is fed back into these two gates, because of the property of these NAND gates, they constantly change, the inputs keep constantly changing, the output keeps constantly changing, the outputs keep changing constantly. Now, this flip flop has a clock low when this clock is high. So, when this clock is high, this clock is low. When this clock is low, whatever is the input does not going to affect the output, because the output is going to stay same, the previous state, so memory state, when the clock of a flip flop is a low. So, when this flip flop is enabled, or the clock of this flip flop is enabled, the clock of this flip flop is disabled. Any change that is going to occur is going to happen here, but occur here anytime it can happen, but only when the clock has completely changed from high to low here, which means it will low to high here, whatever the output here will now go into this. So, the output of this flip flop goes into the input of this flip flop, and it will change the output of this flip flop when the clock is low, the original clock is low. But at that time when you feed back, the changed signal cannot affect this gates, the output of these gates cannot change now, because at this time the clock is low here. So, the change from the feedback, the output fed back into the input cannot affect the operation of the circuit until the clock changes into 1 again. So, that means I am preventing this continuous variation. The variation can only be once. When the clock is high, any change that can happen in this flip flop can only happen in the locally. That local change will be transmitted to this flip flop only when the clock of this flip flop changes into high, at which time this is closed. So, any change that can happen because of this change at the output will be fed back, but will not be recognized until the clock changes back to 1 again, the original clock. So, I have a 2-stage flip flop, basically with the one stage clock being high and the other stage clock being low at a given time, and after some time the first stage clock becomes high, low, second stage clock becomes high. So, that way I am isolating the input fluctuations from the output, or output changes will not be reflected in the changes in the input stage. Such a combination is called a master slave combination. I already wrote the name on the top. This flip flop is called a master flip flop, this flip flop is called a slave flip flop. The slave can only take the master's output and convert into its own output, but that can happen only when the clock is enabled for the slave. When the clock slave is enabled, already the master clock is disabled. So, slave change, the output of the output change in the slave flip flop will not affect the master output until the clock of that flip flop becomes high, which is only when at the end of that period of off period for this clock. So, I mean that means we are now making sure that changing from Q to Q bar when S is equal to 1 or R is equal to 1 will still happen, but only once in a clock period when the clock is high, when this master's clock is high. Now, instead of this toggling that we saw, this is the clock, we will say only master clock as a function of time goes from 0 to 1. Master output originally would have been like this, that is because of the feedback. Now, the feedback is not there. So, the change of whatever it was, it will go, if earlier 0, it will become 1, and then it will continue to be 1 until again it becomes 1, at that time it will become 0. So, this change over from 0 to 1 to 1 to 0 will happen, but only once during a clock period. So, the output of the slave will be only this change will be reflected into the output only at the end of this clock period. So, that will be when here during the positive edge and slave would be at this point the slave clock will be low. When the master clock is high, slave clock is low. So, the change in the master cannot go to the slave. At this point the slave clock becomes high. So, when the slave clock becomes high, only then the master change in the master output will be recognized by the slave. So, the slave clock would be working like this. I mean slave output will be delayed by this clock pulse period. So, the output keeps changing from 1 to 0 also here in this case, just as in the case of the previous circuit we discussed the last lecture. Constantly toggling is not there, it changes only once in a clock period. This is a toggling mode really. As I said, toggling is a control change, raising is an uncontrolled change. Toggling is useful, we will see that later on how it is useful. Raising is not useful, raising is undesirable. That means I have eliminated now S is equal to R is equal to 1 problem which I had in the original SR flip flop. The original SR flip flop 1-1 condition was not to be used because of certain unreliability, undefined performance, uncertain performance. We want to remove that, but we ran into a racing problem. The racing problem is solved by putting an extra flip flop. So, this is a master slave configuration. It can work for any type of flip flop. D flip flop also can have a master slave. SR I have now made it like this. D also can be master slave. You can have 2 flip flops with 1 clock connected, the master slave, master clock and slave clock with phase inversion. Such a configuration is called a master slave configuration. Does not have to be for only SR flip flop. Now, that means this new flip flop, this tamed, as I said, tamed S is equal to R is equal to S is equal to 1, R is equal to 1 condition. I will now give a new nomenclature because SR flip flop will always bring back the memories of 1-1 being not permitted. So, I do not want to call it a modified SR flip flop or anything. So, this SR flip flop with the feedback and an extra flip flop to extra stage to control the operation, this whole configuration is called as JK flip flop. I do not know why it is called JK flip flop frankly, because they had SR they want to say JK. So, a JK flip flop works like this. J is equal to, so instead of calling this S input, I will call it J input. It's same as S input except for the case of S is equal to 1, R is equal to 1. SR flip flop and JK flip flop are identical. JK flip flop works exactly like SR flip flop for the 3 cases 0 0 0 1 1 0 1 1 0 0 0 1 1 0. For 1 1 case SR flip flop is not permitted, in JK flip flop it is permitted with the toggling output. That is all there is to it. So, SR flip flop plus this additional toggling facility becomes a JK flip flop. So, this is called J and this is called K. So, JK Q Q N Q Q bar, if both are 0, we will also put a clock here. When the clock is 0, no matter what happens with J and K, output is memory state. When clock is 1, 0 0 is memory state, 0 1 is reset state, it means 0 1. 1 0 1 0, this is reset, this is set 1 1 1. So what is Q? We don't know until we know what Q was. Q toggles means what? The previous value of Q is complemented. The present Q is the complementary value, complement of the previous Q. So we will have to say Q is, you can write toggling mode, you write Q bar. So you can't write Q is equal to Q bar, doesn't sort of looks odd. So what I should write is at this clock pulse, if it is nth clock pulse, what is the value of Q for n minus 1th clock pulse will become the value now. So I will call this n. This will be the previous value, Qn plus 1 would be Qn complemented. Qn complemented becomes Qn plus 1, or Qn minus 1 complemented becomes Qn. So this is the toggling mode. So this is a sort of a flip flop in which all the conditions are met. We don't have to worry about 0 0 1 1 being encountered in a circuit as inputs, and toggling has its own use. We will see it later in design of counters. Toggling property has use. So now to summarize, we have now seen an SR flip flop. Of course, we start with the latch. We can store a bit of information and keep it there until you change it. Then we wanted to do it a controlled way whenever we wanted it. That means introduce a clock and say when the clock is high, only the input should be recognized. We did that. So it's a clocked SR flip flop. And then we said we want to put a simple data bit 1 or 0. Why do you need 2 inputs? So we converted an SR flip flop into D flip flop. So D flip flop with the clock, whatever data you put in gets stored. With clock 0, whatever you put in the data does not get in, it remains the same as what it was earlier. And we modified the SR flip flop to introduce the extra gate with a feedback, extra input of the input gate with a feedback, and we called it a JK flip flop, where for that condition of S is equal to 1, R is equal to 1, or in this case J is equal to 1, K is equal to 1, we had the output complementary to what was earlier in the previous clock cycle. And in order to avoid racing, we have to put 2 of these in a master slave mode, the master slave configuration. So this is a JK master slave flip flop, they call it, master slave JK flip flop. With the master slave concept of, if you want to delay in the D flip flop also you can have a master slave operation. If you have 2 D flip flops, one connected to the clock high and the other connected to the clock low at the same time, one value you put here, that value gets stored immediately when the clock is high, but then that D cannot transmit to the next flip flop because the clock of that flip flop is low. When the clock becomes low for the main flip flop, the master flip flop, it cannot take a new value, but the value stored in the flip flop will go into the second flip flop, the slave flip flop, because the clock of that will be high. So I can have the data stored in the second flip flop when the clock is low. If you want that operation instead of want to store the data when the clock is high, and only once it can happen, because once that happens, whatever change I make in the D input, because the master is now 0 clock. So if you want to make only one change in your data per clock cycle, this is the best way to do it. You want to make only one change in the data storage in one clock cycle, in one clock period, you put a master slave configuration. The master takes it, slave will not be affected, whatever happens in the master will be transmitted to the slave at the end of the half period when the clock becomes low from high. At that time the slave takes whatever was the output of the master, but any more change in the master cannot happen because the clock of the master has already become low. So this JK concept to avoid raising can also be applied to a D flip flop, master slave D flip flop is also possible. Wherever you want a data, I said there are 2 ways of making sure the data changes only once in a clock period. One is to make sure the data changes when the clock is low. When the clock is high, do not put the data. That is one way. The other way is to have a master slave configuration. Whenever the data changes, the output will change only once during the clock going from the output clock. Now the second stage clock, second stage data changes when the clock goes from high to low. Same case in a D flip flop, you put a D value, the master will take it during the clock high, but then it will pass it on to the slave, the clock goes from high to low. That is a master slave D flip flop. A master slave is a concept, but it helps to avoid racing in the case of JK. Now I have, so that means we have all the combinations. Simply data putting, we can put a D flip flop, one SR flip flop sometimes, but most probably SR flip flop has no use, because if you want simple storage of data, you put a D flip flop. If you want more than that, the toggling action, you put a JK flip flop. There is no need to have an SR flip flop. Generally SR flip flops are not used that much. They use D flip flop just for data storage purposes, keep it and store it, and whenever you want to get it back, or you want some other thing to do with a flip flop like a toggling action, which I said will be used in counters, use a JK flip flop. These are the two most popular flip flops. Sometimes I want only this toggling action, only the toggling action. In that case, what I should do is I will take a JK flip flop. Now whatever I draw here as JK is the whole thing. These two inputs and clock is only available to, these two inputs and the clock are only available to me, and output Q and Q bar or the slave are only available. Internal feedback, the internal inverse of the clock, all those things are not available to me in a block. When I buy a JK flip flop, I have a single flip hardware where is two inputs for J and K, one input for clock, one output for Q, one output for Q bar. Q and Q bar outputs are from slave, JK inputs are into this master, and clock is there. Inside, internally the clock gets inverted for the slave. Of course, you need to give some power supply. No circuit will work without powering up. You need voltage and ground. You need two terminals, one to supply the give the current voltage called VCC or VDD, depending on whether it's bipolar transistor technology or CMOS technology, and then ground. So I am not talking about power source. How are you going to power up? I am only talking about signals. JK are signals. Output is a signal. Clock is a signal. You have to determine. You have to know the difference between signals and the power source. Power source is required. Any active circuit, we need a power source. Okay, we will not consider power source in this drawing. Usually we will have to put in addition to that VCC and a ground and all that. So JK and clock and Q bar. If I only want toggling action, if I want, I have an input, I have a clock period and I want an output which is always toggling back and forth at the rate of 1 per clock period, then I do not have to go through this SR flip flop type of thing. I can as well connect these two together, because when J is equal to 1, K is equal to 1, I will call this input T input, T for toggle, toggle input. When T is 1, it toggles, when T is 0, memory state. When T is 0, 0, 0. J is equal to 0, K is equal to 0 is memory state, J is equal to 1, K is equal to 1 is toggle state. That is why the input is called toggle input. T is 1, it toggles, T is 0, it does not toggle or it stays, and of course clock is required. So what will be the truth table of this, or characteristic table of a T flip flop? Clock T Q. When clock is 0, output remains the same. no toggling action. Clock is 0, it is a memory state always. All flip flops, clock is 0, it is a memory state. When clock is 1, when t is 0, again it is memory state. Is that right? When clock is 1 high, if I do not give the toggle input, which means it is t is equal to 0, which means j is equal to 0, k is equal to 0, that means it is a memory state. When clock is 1 and t is 1, then qn is qn plus qn bar. The previous value of qn gets complemented to the new value. The next value of qn is always the previous value complemented. So, this is a toggle flip flop, it is a t flip flop. Sometimes you get a t flip flop, t is equal to clock. These are the two inputs. You have not assume that internally it is a jk flip flop where they have tied t and j and k. That is all there is to it. Like a d flip flop, I said internally s and r are inverted. S inverted, there is an inverter between s and r, then it is called a d flip flop. Likewise, it is called a t flip flop. So, that means there are totally 4 types of flip flops you have seen. A SR flip flop with its own limitation of the 1 condition. A D flip flop where you can only put a 0 data storage and not a toggling action. You put a JK flip flop where it works for both, it works from a D, it works both as a D flip flop and a toggle flip flop. So, one JK flip flop is equal to one SR flip flop or one D flip flop plus one T flip flop, and a T flip flop where only toggling happens. So, that means you can use any of these 4 flip flops for the particular operation or performance or circuit you are trying to design. This extra hardware, this slave hardware, almost doubling the thing in effort in terms of the number of gates hardware. One of our goals, what is one of our goals? We have always been saying 3 things: high speed, low power, low cost or small size. So, that beats that we are unnecessarily putting extra hardware. So, is there any way I can do the same, changing only once in a clock period, but not having to put an extra flip flop, duplicate an extra flip flop? That is one reason why I may not use JK flip flop sometimes. There is another reason why we may not use JK flip flop. We said what is the fastest rate at which the clock can change. The fastest rate at which the clock can change is the time it takes for the propagation delay of the 2 flip flops, in this case 2 flip flops. Any flip flop is a single flip flop. How fast can I change the data and keep storing it or sending it out? At the rate, the propagation delay is the time it takes for the data to travel. Of course, in addition to propagation delay, there are a couple of things called setup time and hold time. We will see these things a little later on in the course. Right now, do not worry about these terms. There is a setup time, there is a hold time and a propagation delay. Let us bunch them all together for this discussion today. We will bunch them all together, and there is some delay involved. Within the delay, I cannot change the input. That means, if I clock it faster than that period corresponding to the delay, then it will not, it is not fast enough to catch up. Any change in the inputs cannot catch up with the output cannot catch up with the changes in the input faster than, if it occurs faster than the total delay of the flip flop, which includes propagation delay, setup time, hold time, all that. When that is the case, of course, in extreme cases only this is a problem. Most of the time we are having today's technology, the speed is so high we do not have enough applications. There are very high speed applications, a few of them where it is not enough, the speed is not nearly enough. That is the reason they go on improving the technology and inventing new and newer circuits. That is because they are always a cutting edge technology, cutting edge application. But most of the applications, today's technology is so good, we do not have to worry about all these propagation delays of flip flops. But still, from a conceptual point of view, from a theoretical point of view, we should know the limitations. So, the limit of the change of clock, the limit at which the data can change is the period of the, and that is the rate at which I can change the clock. If I try to change the clock faster than that, it will not catch up with the data cannot catch up with that. So, if I now put two of them, I am going to be further down, slowed down further. If the propagation of the flip flop or the delay of the flip flop, which can involve several things including propagation delay, is the limiting factor in my operation, there are conditions, applications, places where the propagation delay, we will not call it propagation delay, I said delay of the flip flop, is the limiting speed. It is not going to help me if I have to put two of them, it is going to be reduced by a factor of 2. So, I have to slow it down by a factor of 2, and I am already worried about my cutting edge application where the speed is not enough. Now, if I have a master slave configuration, I need to have to do it at half the speed at which I can. The maximum speed is thumb rule, of course, there are always some extra things coming in here and there, but approximately it is half the speed at which I can work a single flip flop, because there is 2 flip flops, 2 delays. So, that is one reason why we may want to think of another scheme, at the same time not allowing the racing, that is important. Because racing is a very bad thing, because you do not want to have an unpredictable performance. So, without racing and without master slave, is there any way I can do it, so that only once in a period, once in a clock period, the output can change. The second thing is extra hardware I need to spend. So, there is a technique called edge trigger technique. You can make an extra hardware, a little bit extra, not a whole lot of doubling the gate type of thing, doubling the flip flop type of thing, but some modification in the given flip flop can lead to a condition that once a change is made, it will stay, that the change will stay for the entire duration of that clock. Only when the next time the clock changes, it will change again. This is where I want to define something called edge triggering and level triggering. When I said gate is an enabling function, gate has an enabling role, what did I say? When the gate is high, clock is high rather, clock is an enabling gate, enabling function. When I said clock is enabling function, we said when clock is high, flip flop works normally, when the clock is low, flip flop remains in a memory state. Now, within, when the clock is high, the flip flop can change output any number of times. I am not talking about master slave, a normal flip flop, a single flip flop. If I want to avoid that, what I should do is, the change in the output, flip flop output should not be level sensitive, sensitive to the level of the flip flop, it should be sensitive to the transition of the gate function. If the gate is high, if the clock is high, this is clock as a function of time, and this is t 0 1. As long as the gate is high, any change in the input will be reflected in the output. I am talking about single flip flop, not the master slave, remember that. I am making a case for doing a non-master slave flip flop, which will do only once in a clock cycle. Non-master slave flip flop, which will change the output only once in a clock period, because I am going to save time, delay, as well as I am going to save some hardware. So, I am talking about that. So, in a single flip flop, I am talking about non-master slave operation. When I have this is the period for which, during which any change in the input will be reflected in the output. I do not want it, I want only once in that period output to change, based on what was the input at a given particular time. This is called level triggering, level sensitive or level triggering. On the other hand, if I make my flip flop, whatever is the input at the time the input changes from 0 to 1, this is again the clock. The input can be anything here, input can be anything here. When the input, it will recognize the input, it will monitor the input, it will sample the input, they call this, technical term for this is called sampling. It will, the flip flop will sample the input at the time of transition from 0 to 1, and correspondingly decide the output. Any changes occurring within that clock period, whether it is high or low, will not be recognized, output will not change until the next clock transition occurs. Such an operation called edge triggering operation. When I say once in a clock period, only once, not only from 0 to 1, not from 1 to 0. Or I can define from 1 to 0 as my reference point and not from 0 to 1. It should not be do both times, because I want only one time in a clock period. I want one change in the output. The output should change once in a clock period. When that is what I want, I have to make it either sensitive to the rising edge, is called rising edge, going from 0 to 1 is called rising edge, and this is called falling edge. Either the rising edge or the falling edge I can make a reference, there is no need that it has to be rising edge. Some people call it positive edge and this is called negative edge. Even though all voltages are positive. So we are talking about positive logic, where I said 0 level is 0 volts and 1 level is some volt like 5 volts or 3.3 volts. When I say positive edge means going from 0 to 1, when I say negative edge it goes from 1 to 0. So I can make a flip flop sensitive to my positive edge alone. Whatever input occurs, whatever input happens to be there in the input terminals, whatever signal happens to be the input terminals at the time of the positive edge transition, that will determine the output for that clock period until the next positive edge occurs. That is called a positive edge triggered flip flop. Likewise, whatever input happens to be at the input terminals, whatever signal happens to be the input terminals at the time of a negative transition from 1 to 0, only those inputs will determine the output of that flip flop for the entire duration of that clock period until the next negative edge occurs. Such a flip flop is called a negative edge triggered flip flop. So, for example, if the input keep changing here, again here, this is called positive edge. On the other hand, if the input keep changing here, clock 0, 1, t, all are functions of time, and all these points are called negative edge points. All these points are called positive edge points. So, if I let my flip flop, or if I design the flip flop, not letting it, if I design my flip flop such that input changes will change the output based on, of course, the condition. Every time there is a positive transition occurring in the clock, such a flip flop is called a positive edge triggered flip flop. Input changes will set the outputs. Every time there is a negative edge occurring in the clock, such a flip flop is called negative edge triggered flip flop. There we have now solved the problem of toggling, because toggling can happen only when the level is level triggered. As long as the clock is high, it keeps racing. We have solved the problem of racing, because racing occurs when the clock is high and it keeps shuttling back and forth. Since you can only change once, there is no question of racing. So, racing can be avoided by positive edge triggered flip flop or edge triggered flip flops. Plus, we do not have a two flip flops like a master slave. That means to that extent I can make it faster, the whole flip flop operation, because there is only one delay I have to reckon with. But of course, it does not come free, that you can't just take a flip flop and do it. You need to have some extra logic built into your original flip flop. The original flip flop, whether it is a T flip flop or a D flip flop or a JK flip flop, generally a D flip flop they do it. In a D flip flop, because JK flip flop is the master state, most of the time JK flip flop is the master state flip flop because of the condition and feedback and all that extra. Generally master state flip flops, JK flip flops are master state flip flops, D flip flops are edge triggered flip flops. The reason is JK flip flop toggling condition is more important. They want to use it for toggling conditions. I am doing something meaningfully with the toggling, which is an application, and such application need not be very fast really, because it can need be fast but need not be very fast. This is a data storage application. D flip flops are data flip flops. As I said, you put a 1 and it stores, put a 0 and it stores. You like to do it as fast as possible in a computer and something like that environment where we need to memory has to be accessed very fast. The data has to be put in at a very fast rate and retrieved at a very fast rate. So they usually use edge trigger flip flops or D flip flops and master slave operation with JK flip flops. It is not restricted, but generally you can have a master slave D flip flop, no problem. Now this way I have the input can change any time, but at the given edge only it will be recognized and the output will change correspondingly. And the extra logic which is required to modify your D flip flop, original D flip flop with the extra modification, some gates, extra gates which will block. What really happens is not very great thing. It blocks the variation because of the nature in which the gates are connected. Once the variation occurs from 0 to 1, it remains at that time unless there is another one 0 to 1 transition occurs. So we look at the circuit, you can analyze the circuit and see why, see for yourself why this change can occur only once during that once during that clock period. That means the circuit is designed as that only as transition from 0 to 1 in the case of positive edge or 1 to 0 in the case of negative edge can change the input to the flip flop. Finally the input is that SR latch. Remember that back to back connected NAND gate, that is always be there in the D flip flop, is not? That is the core. We started with that core. Back to back NAND latch, 2 NAND gates connected back to back. If the input does not change for that, then nothing can happen. Whatever is the input change they have occurring, whether the clock is high or whether the clock is low, and any change in the input cannot affect the output as long as the input to those SR flip flop does not change. And that is what will happen in case, but the extra logic I am talking about, you have to have some extra gates which will prevent these changes occurring except in the case of a 0 to 1 transition in the case of positive edge, 1 to 0 transition in the case of negative edge. I am leaving this as a reading exercise. Please go over some book, standard textbook, in which they will tell you the configuration of a edge triggered D latch, edge triggered D flip flop. There is an extra logic involved. Please try to understand that logic. Please try to first locate that circuit and then understand the operation of that circuit and why that change of the input change 0 to 1 to 1 to 0 only is required, only can make a change. The clock changes 0 to 1 or 1 to 0 only can change the output. That is because, as I said, it blocks the variation within that period. It blocks the variation to the input of that final latch. The final latch is the SR back to back NAND latch. That latch input should remain constant for that whole clock period, whatever happens elsewhere. Why that happens? The way in which the logic is designed, it makes it possible. I leave it as a reading exercise assignment, reading assignment to you. Look at a standard textbook, any book, in which they will tell you the concept of edge triggered flip flops, give you a circuit diagram, look at the circuit diagram, understand the circuit diagram, how it works, and also analyze why this is behaving the way it is. We have now seen 4 types of flip flops, as I said, D flip flop, SR flip flop, T flip flop, JK flip flop. Using them, what we can do, we will see from next lecture.